from Vanderbilt University, and I will be talking about performing high-throughput comparative genomics using a Chado backend. So first off, I'd like to talk to you a little bit about our lab, which is the Rogus Lab. We're a computational genomics laboratory, and we have two main themes, first of which is the fungal genetics theme. And the other theme, which is just a new project that we have just recently started, is investigating the genetic causes of human preterm birth. So RogusDB is our comparative genomics database, and it has over 200 eukaryote genomes loaded. And it's currently running a modified version of the Chado schema, which, yeah, it's actually been pretty great for most of the things that we want to do, but kind of want to talk to you today about a few of the changes that we'd like to see to help our research a little bit. So as a comparative genomics lab, one of the things that we're very interested in measuring is this is genomic similarity. So the simplest form of measuring this is simply just sequence similarity, the most classic algorithm, of course, being BLAST. And once you have BLAST results like this, you can take that a step further and then do some sort of ortholog estimation. So this is kind of just a figure from the Ortho-MCL paper, where it just shows how you can infer orthologs or estimate orthologs, because it's not necessarily the case, and these are just predictions. Orthologs representing, well, theoretically shared ancestry, but often in practice shared function. So once you have these orthologs, then you can do sort of higher order analyses using this sort of information. So an example of that is conservation of synteny. And here, this is just a figure describing how the ST metabolic pathway was horizontally transferred from Podospora into Aspergillus nidulans. And this was proved by the syntenic conservation between these two gene clusters. But another higher order measure is this idea of functional similarity. So these are three intracellular bacteria, and they're obligate intracellular bacteria. And so this is just the glycolysis plus citric acid cycle, and anything in red is representing loss of that function in the organism. So since these are obligate intracellular organisms, they actually depend on their host for a lot of these processes. And so you can see Buchnera has lost almost all of the citric acid cycle, only this succinyl-CoA to alpha-ketoglutamate step. And whereas something like Wigglesworthia has most of the pathway actually intact, funny enough, only lost the forward reaction of the diphosphor-diesterase. But even though each of these genes, they're all orthologous, because you have this loss in this pathway, their metabolism is actually drastically different, despite sharing a lot of similarity otherwise. So once you've done this sort of analysis, often you're going to represent your results as a tree. So this is a beautiful figure from the interactive tree of life, where you have bacteria, archaea, and eukaryota. But this is just a great example of the challenges that come from having to interpret this kind of data. So if you ask a student who has just been introduced to what a phylogenetic tree is, and you ask them, compare the distance from humans to flies against these two yeast. Well, the first thing that they're going to do is they're going to look at all these internal nodes, and they're going to be like, well, obviously, Homo sapiens and Drosophila are widely diverged. So a slightly more experienced student will then realize that only the vertical branch lengths matter. So then they'll look at these two and be like, well, actually, they're about the same. But what the real fact is, if you look really, really carefully, and you measure these branch lengths really carefully, it turns out the Saccharomyces branch, it's actually quite a fast-evolving branch. So the distance between Saccharomyces and Schizosaccharomyces is actually, they're more divergent than humans and fruit flies, which, I mean, from just an initial impression from looking at this tree, it's quite misleading. You could easily get this confused. So this sort of difference then, well, I mean, first off, there's the bias, it's the fact that there's only 3 fungi, but the difference that I'm kind of trying to get at is the difference between phylogeny versus similarity, where phylogeny is this concept of shared ancestry, so the Darwinian concept of homology, whereas similarity is kind of getting at the concept of common function, which is the pre-Darwinian Owenian homology. So Owen was the guy who first coined the term homology. And phylogenetic trees are excellent representations of evolutionary history, but whereas a lot of times when people are looking and using trees, they're not necessarily trying to determine the precise evolutionary history. What they're usually more interested is the relevance of, let's say, a model organism to a specific system that you're studying. And that is actually more dependent on similarity. And this is a good example in the tree of these vertebrates. You can see that crocodiles and birds are actually, ancestrally, they had a common ancestor. Whereas if you asked, most people, whether you think crocodiles are more related to birds or more related to lizards, most people would tend to say lizards, mostly because in recent history, crocodiles and lizards have kind of evolved towards similar lifestyles. So then the question is, how do we quantify and visualize genomic similarity? So I'd like to introduce this concept of a genome yardstick. So a genome yardstick, well, what is a yardstick, first of all? And according to the Oxford English Dictionary, it is what you could say as a standard of comparison. So in this case, our standard of comparison is the similarity between the human genome and other species, which then you can use to contextualize the similarity between 2 arbitrary genomes. So this is just an example of a fake human yardstick. This is not actual real data, but you would expect, okay, so over here, this is the query, so this is the human genome, and of course, it is completely similar to itself. And then its closest neighbor in this representation would be chimps. And then you would see like arthropods, and then nematodes, and cnidarians, and then perhaps a fungal outgroup, all the way at the very end. And what you could do then is you could actually compare this to, let's say, a Saccharomyces yardstick. So this is yeast, and then its closest neighbor then you would expect to see some Aspergillus, and then you would see Basidiomycete, Zygomycete, and then like an outgroup all the way at the end as a chytrid. So the cool thing here is, or well, I guess the important thing here is to realize that the distances are all in relation to the query. So these 2 relative distances aren't, you can't just measure them. You would have to look at the chimpanzee yardstick to see what the difference between chimps and arthropods actually was. So this is kind of like almost a flattened tree representation. And the real goal of this analysis is to quantify the molecular phenotype of the organisms that are used to generate the yardstick. So I'm going to now deep dive into our methods here. So the most, on like a general high level, this is a representation of our database. These dark circles are genomes that have already been loaded, and these are the dark lines of analyses that have already been performed. And then when you input a new genome, then the database tracks which analyses need to be performed. Then you dump out the algorithm input, and then you run it in highly parallel fashion across a compute cluster, and then return that data back into the database. So applied to our BLAST protocols, so our Rogus Lab user would then take their genome of interest, use genome import, which is an import script that I have made to handle the import of really just genomes in general, but specifically poorly formatted old classic genomes that often have a lot of formatting issues involved. So it loads this into the Chado schema, which then we have an audit table that tracks anything that has been updated. And then you can then use what another piece of program that I wrote called the BLAST SQL client, which then it looks at this table, and then it'll dump out the FASTA files that are necessary for BLAST. And then you can also then ask it to add jobs to this pending BLAST table, which are, it's just a list of the blast jobs that need to be performed. So then you can go and then you run the same client on a cluster node, where you actually run the blast analysis, and then it parses the blast output and then returns it and inputs it back into the database. Just a really simplified, big overview. So once you've got the blast hits in the database, then what you do is you want to score the best hit of every gene to every other genome. So these arrows are the best hits, essentially. Each gene is pointing to its best hit. And we took, for this first analysis, we took two metrics. The first would be protein sequence identity, and then a matrix-adjusted protein identity, which is simply the blast hit score. You could also do, and this is kind of next on our list, you could do orthology estimation using a reciprocal blast hit. So here we removed all the hits that weren't reciprocal, and then in that case, then the score would be 1 for there's an RBH, and 0 for this guy, where it doesn't have any RBHs. So what you can do once you have these individual scores is you can average them and to create this aggregate proteome similarity score. So for each pair of genomes, you just find the average by each measure. And so then using that, then you have this graph, which then to generate the yardstick, you would take just a single genome and then all of its neighbors. And the weights of the edges would correspond to the lengths on the yardstick. So these are the preliminary results that we have from using first the aggregate protein sequence identity yardstick. So these are two aspergilli, Aspergillus fumigatus and Aspergillus flavus. And as expected, they're reciprocally very similar to each other. They're nearest neighbors on the yardstick. Then here, this first cluster right here are the other Eurasiomyces. So that is nice to see this taxonomic grouping. Then right here, you get this big mess, which honestly, it's really more an indication of that protein sequence kind of falls apart as a measure of divergence once you get to 0.3 similarity. There's not much signal left here. Although interestingly, they both share this distinctly very distant outgroup, which is E. caniculi, which is an oligopathogen, which has a much reduced genome. So there's essentially very little to align with here, and that's reflected in these distance scores. So then if you take a look at this same idea, except using BLOSUM62 to adjust these values, you see most of the same thing, although I just kind of want to bring your attention to this area. So in the previous, just the identity, see how they're like a little more clumped up, and then you get a little bit better resolution here using BLOSUM62. And interestingly, this is right at the 60% divergence mark. So it would be interesting to see these results using BLOSUM80 or BLOSUM20 and see how that will shift these measures. So this is a method that you could apply to in a variety of different ways. You could, first off, you could restrict your input genes to just a subset of the genome, and so you could form like a metabolic genome yardstick or a developmental genome yardstick where you take transcription factors, and they would be useful for asking certain questions about similarity between these organisms. You could also do tissue-specific yardsticks where you could ask, I want to see what the placental genes in these two organisms and how divergent are they. And you could do the same with embryonic development. So I've been talking a lot about single gene comparisons now, and I just want to dive briefly into pathway-centric yardsticks. So there's this is just a quick overview of this method called gene set enrichment. It's originally purposed to analyze microarray data, but you can actually apply it to any genes in which you have a list of ranked genes and their correlation with their phenotypes. So here there's just a heat map of the correlation with each of these classes, which can be essentially anything that you want. In this case, this would be the similarity scores. And then you could take a gene set, and then what you do is you can you can look for this. I'm not going to go into too much detail with this, but it essentially finds how the entire set as a whole performs as with the correlation values. So these can be arbitrary. So normally this would be expression data. So this would be like highly upregulated, and this one phenotype highly downregulated. But you get this enrichment score, and you can use that then to make some sort of pathway-specific analysis. So the problem, though, with trying to do this analysis is that as it stands, the Chado schema doesn't quite facilitate that as well as we'd like. So here's where I kind of have my own little proposal of what I'm tentatively calling a comparative module, which would implement this idea of feature groups, which would just simply allow you to represent and annotate sets of features. And a really nice thing about this idea would be that it would allow you to avoid denormalization of ortholog annotation, so you would have a single place that holds all of the properties for a set of genes. And I mean, this last point is just nice for performance reasons. When you have 200 eukaryote genomes, you start to get really concerned about performance, and being able to access these sets via foreign keys is also a nice bonus. So this is just a quick diagram. So on everything in white is everything that's already in the Chado schema. So we have our CV turntable organisms and features and feature props and all those nice Chado tables. So over here, the first thing we have would be like a group table to hold the actual groups, which would be classified by their unique name, a rank, because, well, it seems to be just around in Chado all the time, and then a type ID. And so then you link these to the actual features via this table, the feature group table, and one of these arrows is missing. This is supposed to link to the feature table. So this is the link to where features are how you tell that the database that this feature is a member of this group. And then you can annotate them with feature group props, link them to the analysis table with analysis feature group, and then you can have relationships between feature groups, and then you can annotate those relationships with the feature group relationship prop. So just, there's probably a few more tables that would need to be added for this to really fit with the whole Chado ideology. I mean, I know that a pub table would also be necessary, among other things. But this is just kind of, I just wanted to throw this out there as a potential idea. Yes?
So I followed everything well up until right here. And I wonder if you could just, maybe this is just for my benefit, say again what the objective is, and this is also, it may reflect my ignorance of sort of Chado details, but what is the problem that you're trying to solve again?
Oh, okay. Well, so normally if you want, well, not normally, but as of right now, probably the only way to really implement the idea of, let's say, an ortholog group in Chado would be you would have to you would have your features, which would hold your actual genes. And then you could annotate each one as a feature prop. It is part of this ortho group. The problem is that the feature prop table isn't actually amenable to that sort of annotation, because the only way that you could store that would be like you would like type it as an ortho group, and then you would put a value as a text value. And then the only way to really discern the differences between each of these would be you would have to, well actually I can just go on to the next slide. So there are some performance problems with that method. So if you use the feature group method, since assuming we've indexed all of our tables with a B tree, then inserting a group is log n, inserting a member, well it's 2 log n, but that's still O of log n. And then selecting all members is once again log n. Annotating really is only just having to make that foreign key reference, so once again log n. And deleting a group is also once again log n. But if you approach this as tagging it via feature prop, so inserting a group, first of all, this exclamation means that you're introducing denormalization in the database. So you're replicating this data multiple times when it should actually be coalesced and represented as a single row in the database. So that's login. That's not horrible. But if you, and selecting a member is the same. But if you wanted to select all members of a given ortho group, you would actually have to go over the entire feature table, look at each of their property, join it with a feature property table, and look at every row. And that's actually linear. And going from sublinear to linear running time is really unfortunate. And annotating a group, once again, you would have to replicate that annotation across every member of your set instead of just being able to have it once for the entire group. And so once again, you introduce denormalization, and then that would also take a linear amount of time, since you would have to go over the entire feature table to find all of your members. And then it's the same with the delete group, and the reason why this is also linear is mostly because the selecting all the members of the group is actually linear running time. Does that explain some of your questions?
So the idea is that we have some biology where we want to treat, we have sets of genes that have kind of, that we think are biologically real sets, right, the orthology. And so we'll be able to handle those sets really easily and with reasonably high performance. And there's no current way of handling the sets over and over again and because we have more than just orthology in mind. This is kind of our primary use case. So we have to have some way of speeding up performance, and we'd like to have the community have kind of a standard way of handling sets of genes. So that way we're not just building our own little hack inside.
Another question.
So this is very interesting and timely to us. So what we've done, so Flybase, but we were chatting about this a little bit, we have melanogaster as our reference genome, and so we just make feature relationships between the melanogaster gene and all the orthologs. But then, in order to to avoid these kind of problems with performance columns, we have to essentially do a denormalization for our reporting database and put it all into a prop anyway. It becomes a table, essentially, the feature prop that gets reported out to our users or put in a file or whatever. So, and not only that, but we've been thinking about this very grouping idea for biologically relevant sets of data that are not orthologous necessarily, but paralogs or functional groupings and so on and so forth. So what we had been thinking about kind of in our, without extending anything, not that I'm against extending by any means, but we use the library tables
to group them.
to group genes together. And that's, one way around it, but it's kind of conflating the whole
Right, because it's not really a library.
Yeah, it's not really.
Yeah, it's actually similar to what I have thought about this problem before too, although I've thought about it in a more general sense in that there are frequently groups of things. You want to create groups of different kinds of things. Well, all groups of the same thing, but maybe I want groups of genotypes or groups of, I don't know, whatever. And so that it might also make sense to have a more generic group, not feature group, a generic group module where you can say, I've got a group and I have this type of thing where you have, oh good lord, a controlled vocabulary where you describe what types of things you might be grouping, and then you could take what you did but make it a little more generic, and then it doesn't have to be groups of features, it could be groups of anything.
I think that's the Perl approach.
I know, that's why it appeals to me.
So one of the advantages, I think, is the foreign keys.
One comment.
You wouldn't have the foreign keys.
I haven't done this gene set, but as I look at the computation analysis module, it says that the same way we group for the blast hits using HSP is create a kind of a fake feature and then group them under them. Is that something? Is this something that's taking care of it?
It could, because I don't like making those fake features to group things.
Yeah.
They're not fake. They represent something. They represent a real concept.
No, there is only one problem with those features. Sometimes, say if you have alignment between different organisms, And then feature table always imposes you to use an organism. I don't know what organisms to use when I have the alignment.
No, and that's right. That's a good
And
point.
I just couldn't, yeah, that's.
Yeah.
The null
So
organism.
is your feature group table that have a link to organism table?
Huh?
So an instance of feature group row, will it have a link to an organism table?
Only through its members, because,
Okay.
so unfortunately, the arrow here is missing to the feature table. But, yeah, so you would have groups and then you would have this association table. And then through the feature table, then you would get to an organism. Because, I mean, groups are, I don't know, how would you assign, like, you know, something like a kinase or like orthogroup or a protein family? It's not really bound to a single organism. So you kind of want that to be almost independent of most of the properties of the individual features.
Not to mention if you actually had an organism ID in your feature groups, then you have the problem with denormalization again, or possibly them disagreeing with the actual features that are contained.
Right.
Yes.
What about the phylogeny module? Because I see there is some orthology paralogy group identifier.
In the phylogeny module?
Oh, with the phylum nodes? So I can see that being used for grouping organisms together, but I don't know, it doesn't seem to really connect too well with the feature table itself. So this was something that I was thinking of specifically for grouping features, and yeah, like what Scott said, it's like, what do you do if you want to group organisms together? Do you have to have this all of these tables except organism?
Replicate. Yeah, exactly.
Yeah, so-
Right, which is exactly the problem I was thinking of when I thought maybe there needs to be some more generic sort of container.
But see, the one problem I was thinking about with that was, I don't think you should be allowed to group a feature with an organism. It would be kind of weird.
Yeah, no, I know.
What does that make sense?
I know.
So,
And like Bob said, the advantage of this is that you do have very tight coupling with foreign keys to the appropriate tables. And
It might be, so feature groups are really big sets, right? So,
Do they have to be?
well, no, what I mean is that in general, right, so features are where you store just about everything that's sequence related, and that's where a bulk of your data is in a lot of cases. So having something that's optimized for performance, for features specifically, makes a lot of sense. Whereas if we wanted to have a generic version of groups for less data intensive sets, it might be of doing both. Obviously, it's kind of a pearlish way of doing things where you can shoot yourself in the foot or both feet simultaneously.
Yeah, I mean, so the library right now has an organism ID, or else it would be,
right.
rename the library table or something else, like a group, and it would be.
Because I really do like Scott's.
The generic thing.
Yeah, I do like Scott's suggestion of having a generic ability to group anything. But I think that because of the foreign key issue, that perhaps having a specific set of tables just for the features specifically might be worth doing.
So a couple generic kinds of relationships in biology are things on a chromosome, and that generates sort of shallow hierarchies with respect to a primary reference feature. And Chado seems to be designed primarily around that. Another kind of relationship is deep nested hierarchies, the kind of things that you have in phylogeny. I don't know the database theory, but would a triple store or a graph database, would that be better suited?
Yes.
I think someone needs to do that.
They have,
Who did?
the owl people.
well, doesn't every row have an entry in the DBX ref table? Or
Every
somehow
row,
it relates
in
to
feature, you mean?
what?
What every row everywhere? I'm
Yeah.
not sure what you're asking.
No? Okay. I see. The one part of Chado that really confuses me is DBX ref table, but it seems like everything somehow relates back to it, and maybe you could make groups of those to have just rows of arbitrary rows in the database and group them together.
So if you had a generic group, it would have a group type, and one group type could be feature group, right? And another one could be chromosome position type or taxon type. And you could have groups of groups too to generate the hierarchy kind of thing.
But,
That's your point back, right?
yeah, but then you need a linking table size. Yeah, whatever kind of group.
Right, provide the foreign keys.
Yeah,
That's
that adds.
Well, you could just use database arc, and then you don't actually
database what?
database arc, whereby the table specifies which table parameter key links to.
Oh god, make my head hurt.
It's how you keep your table numbers down. So, but then you have to know how the data is structured,
Yeah.
as opposed to actually to follow from the schema. So it does work.
Okay.
But most databases can't enforce referential integrity.
Yeah, that's
That's the only issue with it.
This was question all that.
You can do it by Oracle. I don't know.
okay. Anyway, I guess we should.
Yeah, well, just so I hope that I've convinced you that these genome yardsticks can quantify similarity between organisms, and that these specialized yardsticks could test the relevance of model systems, and that we really, really want a way to handle sets of genomic features that is standardized, agreed upon everyone, and of course it's going to be really hard. It would be something that we would really love if it was part of Chado. So, and with that, I would like to acknowledge my PI, Dr. Antonis Rokas. He is the main intellectual force behind this idea of the genome yardstick, and of course Dr. Chris McGarry, who's here with me today, and another postdoc in the lab, Dr. Jennifer Wiskaver, who really helped me make some of these figures. It would have been quite difficult to give this presentation without her help. And of course I want to thank the GMOD project for all of the tools that they have just so graciously provided to us for just, just almost nothing essentially, and the March of Dimes premature birth grant that is currently funding one of our major projects in the lab.
Great. Thank you. You do have some interesting graphics. I like your graphics. Do you have any other, maybe quick questions or anything? I mean, this seems like we've...
One of the things that stands out to me is that this could actually apply very easily to spectral acquired mutations across different species, because we're sequencing dog, human, mouse, yeast, everything. If we can do the links of this exon of this gene is the same as this exon of this gene, and show that the same mutations are occurring in multiple species on the pathway, this would work well for linking that sort of stuff together. I suspect our Cosmic database has some intent doing something similar. It only works on single transcripts of genes, so there are flaws in how that historical system will be graded. So there's possibility certainly that we would be starting to look into this as we move into more species.
I think that's the direction anything genomic is going, right? You sequence everything out, and we're going to have lots of closely related organisms, or same multiple genomes within a given organism. And I think we're
one more comment. Neat idea of the genome yardstick. One other way you could derive these yardsticks would be to basically traverse a phylogenetic tree, consensus phylogenetic tree, say. And if you did that, say, on one that was derived from synonymous sites, and then again, non-synonymous, then you could look for branches that were under positive selection, for example.
Yeah, we so definitely the thing about comparing the distance of the phylogenetic tree with just the similarity. You can line up two yardsticks and then look at off diagonal things, which would be where organisms differ, But I think using the synonymous distance versus the non-synonymous.
No, I like that idea a lot.
Okay. All right, well, very good. Thank you, Barb. All right, so next up we have our keynote speaker, Andrew Su, has very graciously agreed to come and give us a talk. Andrew and I chatted about at least